Today we will discuss convolution theorems, applications of convolution theorems. First example, find the inverse Laplace transform of 1 upon p plus 1 p square plus 1 by convolution theorem. First is this one fp. Fp is equal to 1 upon p plus 1 and gp is equal to 1 upon p square plus 1. Inverse Laplace transform of 1 upon p plus 1 is e minus x, and inverse Laplace transform of 1 upon p square plus 1 is sin x. By convolution theorem, inverse Laplace transform of fp dot gp is equal to integral 0 to x fu gx minus u du. 0 to x fu gx minus u du. Inverse Laplace transform of 1 upon p plus 1, 1 upon p square plus 1, 0 to x e raised to power minus u sin x minus u du. F function f is the fx is this one and gx is this one. Therefore, the inverse Laplace transform of multiplication of two functions will be equal to integral 0 to x e raised to power minus u sin x minus u du, or 0 to x e raised to power minus u sin x sin u cos u minus cos x sin u. Sin x, cos x, these are constant functions. We have to integrate with respect to u. Therefore, sin x 0 to x e raised to power minus u cos u du minus cos x 0 to x e minus u sin u du. Sin x, integrating by parts, e raised to power minus u minus cos u plus sin u upon 2. Limit 0 to x minus cos x, integrating by parts this one, e raised to power minus u sin u minus cos u upon 2, 0 to x. Sin x upon 2 e raised to power minus x, putting the limit 0 to x, minus cos x plus sin x plus cos 0. Cos 0 is what? Minus cos x by 2 e raised to power minus x minus sin x minus cos x plus cos 0 is 1. This and this will cancel. E raised to power minus x by 2 common, sin square x plus cos square x plus half sin x minus cos x. Sin square x plus cos square x is equal to 1. E raised to power minus x by 2 half sin x minus cos x. Half e raised to power minus x sin x minus cos x. Next application, find the inverse Laplace transform with the help of convolution theorem 1 upon p square into p plus 1 whole square. Here fp is taking this one as fp 1 upon p plus 1 square and gp is 1 upon p square. Inverse Laplace transform of 1 upon p plus 1 whole square is equal to e minus x inverse Laplace transform of 1 upon p square, or inverse Laplace transform of 1 upon p square is equal to x. Therefore, inverse Laplace transform of 1 upon p plus 1 whole square is equal to e minus x into x. Laplace transform of 1 upon p square is equal to x. Hence, by the convolution theorem, we have inverse Laplace, the statement of convolution theorem. Inverse Laplace transform of fp into gp is equal to 0 to x fu gx minus u du. 0 to x u, fu is this one, fx is x e raised to power minus x. Fx is equal to x e raised to power minus x. Therefore, fu is equal to u e raised to power minus u. And this is x minus u. Now 0 to x ux minus u square into e minus u du. Integrating with respect to u by parts. First function taking this one as first function, second function. first function, integration of second function, limit 0 to x plus differentiation of first function into integration of second function. This will become 0. When we put x, u is equal to x, x square minus x square 0, and when we put u is equal to 0, this will become 0. X minus 2, again integrating this one by parts, x minus 2u e raised to power minus u upon minus 1. First function, integration of second function, limit from 0 to x. 0 to x, 0 minus 2, differentiation of this one, integration of this one. When we put x, u is equal to x, x minus 2x e raised to power minus x, minus minus plus, plus when we put x, u is equal to 0, this will become 0, x, plus 0 to x, 2 e raised to power minus u du, x e raised to power minus x plus 2 e raised to power minus u upon minus 1, integrating this one. This will become x plus 2 e raised to power minus x, x minus 2. The next application, the convolution theorem, is to prove that beta function, beta mn, will be equal to 0 to 1, x raised to power m minus 1, 1 minus x raised to power minus raised to power n minus 1 dx is equal to gamma m plus n, where m is greater than 0 and n is greater than 0. Both the m and n are positive. Hence, reduced as 0 to pi by 2 sine 2m minus 1 theta cos 2n minus 1 theta d theta gamma m gamma n upon gamma m plus 1 is equal to 1 by 2 beta m n. Solution. Let fx is the definition of beta function, convolution theorem, 0 to x u raised to power m minus 1 x minus u raised to power n minus 1 du, where fx is equal to un minus 1 and gx is equal to u raised to power n minus 1. This is the convolution of two functions f star g. Hence, by the convolution theorem, fx is equal to Laplace transform of fx is equal to Laplace transform of fu in star gu, or Laplace transform of f into Laplace transform of g. Laplace transform of x raised to power m minus 1, fx is this one and gx is this one. Laplace transform of this one, x raised to power n, will be equal to gamma n factorial n upon p raised to power n plus 1. Therefore, the Laplace transform of x raised to power m minus 1 will be equal to m minus 1 factorial upon p raised to power m into n minus 1 factorial upon p raised to power n. Or we can write this one as gamma m gamma n upon p raised to power m plus 1. Fx will be equal to, here fx will be equal to gamma m gamma n inverse Laplace transform of 1 upon p raised to power m plus 1, or gamma m gamma n inverse Laplace transform of this one, Laplace transform of 1 upon p raised to power n plus 1 will be equal to x raised to power n upon factorial n. Therefore, this Laplace transform, inverse Laplace transform of 1 upon p raised to power m plus 1 will be equal to x raised to power m plus n minus 1 upon m plus n minus 1 factorial. Gamma m gamma n upon gamma m plus n x raised to power m plus n minus 1, replacing x by 1. f1 is equal to gamma n upon gamma m plus n into 1, m plus n minus 1. or f1, the definition of fx is 0 to x fu gx minus u du. Therefore f1 is equal to 0 to 1 u raised to power m minus 1 1 minus u raised to power n minus 1 du, or we can write this one as beta mn. Therefore beta mn will be equal to gamma m gamma n upon gamma m plus 1 is equal to 0 to 1 u raised to power n minus 1 1 minus x raised to power n minus 1 du. This is the Laplace application of inverse Laplace transform to evaluate beta function. Now deductions. When we put u is equal to sine square theta in the integral, this one beta mn is equal to 0 to 1 u raised to power m minus 1 1 minus u raised to power n minus 1 du. When we put u is equal to sine square theta, then the limit becomes, when we put u is equal to 0, sine square theta is equal to 0, therefore theta is equal to 0. 2. When we put u is equal to 1, sine theta is equal to 1, or u theta is equal to pi by 2 or 90 degree. The limits becomes from 0 to 1 to 0 to pi by 2, and put u is equal to sine square theta, therefore sine theta 2 raised to power m minus 2. And second one, 1 minus u means 1 minus sine square theta is equal to cos square theta. This will become cos theta raised to power 2n minus 2, and d theta du will be 2 sine theta cos theta d theta. Sine theta, adding this one, cos theta, adding these two. Beta mn is equal to 0 to pi by 2 sine 2m minus 1 theta cos 2n minus 1 theta and d theta. Or we can write 0 to pi by 2 sine 2m minus 1 theta cos 2n minus 1 theta d theta is equal to half of beta mn. This is the application.